Hello, everyone. This is Kyle Welch with RCR Wireless News. I want to thank everyone for attending Understanding and Testing Carrier Aggregation in the Field, presented by Rohde Schwarz. Our presenters today are Paul Denisowski, Application Engineer at Rohde Schwarz, and Jeremy Cline, Application Engineer at Rohde Schwarz. And at this time, I'd like to turn the presentation over to Paul.
So hello everyone and welcome to our webinar. I'm going to start with what I hope is the brief history of LTE. I'm going to make the hopefully safe assumption that everyone on this webinar has heard the abbreviation LTE. In fact, I think it would probably be safe to say that thanks to many, many millions of dollars in marketing and advertising, pretty much every man, woman, and child over the age of 5 in the United States has heard the abbreviation LTE. Now, in popular usage, LTE is often referred to as 4G. The G referring to generation of cellular technology. The previous generations being, of course, 3G, UMTS, WCDMA, EVDO, or 2G, things like GSM or CDMA2K. AMPS, the Advanced Mobile Phone System, was the first generation of cellular technology in the US, but obviously no one actually called it 1G at the time. Now, from a standards point of view, the initial release of LTE was called Release 8, and this release defines the bulk of what most of us consider to be LTE. This includes very low-level things such as modulation, coding, etc., all the way up through system information, signaling messages and procedures, etc. The next release was, as you might expect, Release 9, but this is really more of an addendum to the original LTE release. Now, many of the features in Release 9 are not really visible to subscribers, things such as dual-layer beamforming and self-organizing networks. Many of these features have not even been widely implemented. About the only feature actually in Release 9 that subscribers might be explicitly aware of is what's called PWS, the Public Warning System, which causes your phone to provide notifications. Sometimes these notifications are quite loud, as a matter of fact, of things like flash floods, tornadoes, etc. in your area. Now, as opposed to Release 9, Release 10 is also known as LTE Advanced, and this is a much larger step forwards in terms of features and functionality. Again, many of these features are more important from a network and device design point of view rather than from a direct end user point of view. These include things such as support for heterogeneous networks, PETnets, higher order MIMO schemes, etc. Now, the most important features in Release 10 is, as you might have guessed, carrier aggregation. And this is the one that will have the most immediate and most important impact on the function and performance of LTE networks going forward. One note I'd like to make at this point is that many of you have probably heard of VoLTE or Voice over LTE, which enables voice to be carried natively over LTE networks, as opposed to dropping back to 3G for a voice call. While there are features in the LTE standards that have been designed to help support VoLTE, VoLTE itself is not actually a feature of any specific LTE release. So why introduce the concept and the complexity of carrier aggregation? What makes it attractive to network operators, device manufacturers, and of course subscribers? The simple answer is that LTE has been a victim of its own success, so to speak. In the 3G and especially in the 2G world, data service was typically seen as something of an extra. I mean, sure, you could access websites from your cell phone and maybe download a file, but it was slow, cumbersome, and expensive. No one in their right mind would try to watch a YouTube video at 2G data rates. With the advent of LTE, people rapidly became used to the idea of consuming rather large amounts of data on their smartphones. The converse of this is that once you raise the data rates even higher, and these higher data rates were available on mobile devices, applications were then developed to leverage these higher data rates. And this in turn created an even higher level of data demand. LTE has effectively raised everyone's expectations regarding mobile data service levels, and ironically, this has begun to create sort of a capacity crunch in areas with high subscriber density. Now, there's been a long and proud tradition of solving these kinds of problems by throwing bandwidth at them, mostly because throwing bandwidth at the solution usually works pretty well. Certainly, this has been the case in the wireline world, where you often have the option of buying a bigger pipe, so to speak, than you could ever hope to actually fill up at your residence or at your business. In the cellular world, however, this is a problem for two reasons. First, spectrum is a finite resource. You can't address capacity issues by laying more spectrum the way you can lay more fiber in the wireline world. In addition, the spectrum allocations available to cellular network operators are scattered all over UHF. The other reason is that in order to preserve backwards compatibility with hundreds of millions of existing LTE devices, you can't simply define new LTE bandwidth of, say, 40, 80, or 100 megahertz, even if you did have a contiguous spectrum needed to have an allocation that wide. Now, before we plunge into the details of carrier aggregation, we need to talk a little bit more about the role of bandwidth, or precisely bandwidths, in LTE. As many of you probably know, LTE is unlike previous radio access technologies in that it supports wider carrier bandwidths, up to 20 megahertz, and a wider range of bandwidth, so 1.4, 3, 5, 10, and 20 megahertz. Here in the United States, the initial LTE deployments at 700 megahertz were mostly based on 10 megahertz carriers. But over the last few years, we've begun to see much more diversity in terms of bands and bandwidths used for LTE, especially here in the United States. Now, as I alluded to on the previous slide, it's probably no surprise to anyone that more is better when it comes to bandwidth. Wider bandwidths mean higher throughputs and higher capacity, and this in turn translates to a faster network, especially from the subscriber point of view. Now, as I mentioned at the beginning of this webinar, LTE has, in a sense, become its own worst enemy in that it's created a tremendous growth in the demand for bandwidth. So how do we then get more bandwidth given fragmented spectrum allocations and the needs to be backwards compatible with Release 8 devices? Well, it's very simple. We combine or aggregate multiple LTE carriers. In essence, we're stitching together multiple LTE carriers and treating them as a single larger carrier in order to obtain the benefits of wider bandwidth. It's really a very clever scheme, since in addition to acknowledging the non-contiguous and somewhat haphazard distribution of frequency bands around the US and around the world, it also preserves backwards compatibility. An older Release 8 or Release 9 LTE device that knows nothing at all about carrier aggregation simply sees normal single LTE carriers. Now, as you might imagine, this is not nearly as simple as it sounds, and there are numerous things we need to be aware of when we're deploying, testing, and troubleshooting LTE networks that are using carrier aggregation. In LTE Advanced, the individual LTE carriers are referred to as component carriers, often abbreviated as CC. These are normal, vanilla Release 8 carriers and can be of any of the supported LTE bandwidths, so anything from 1.4 megahertz all the way up to 20 megahertz each. The standard actually allows up to 5 component carriers. Once we begin talking about the carriers in the context of carrier aggregation, we have to designate which one of these will be the so-called primary component carrier, or PCC. The remaining carriers are then referred to as secondary component carriers, or SCC. Now, in the same manner as in regular FDD LTE, carriers are either downlink, so tower to phone, eNode B to UE, or uplink, phone to tower, or UE to eNode B. And Release 10 allows you to mix and match carriers any way you like. You could, for example, have 2 uplink and 2 downlink carriers. That said, the expectation is that the vast majority of deployments will be asymmetrical. That is, there'll be more downlink component carriers than uplink component carriers. This makes perfect sense if you consider the nature of how most bandwidth is exchanged. A small amount of data is used to request a large amount of data, such as a web page, file, video, etc. But again, there's nothing specifically in the standards that specifies how these carriers are to be assigned and used. This is, to a certain extent, left up to the individual network operators. There are 3 basic ways, however, in which these component carriers can be distributed in spectrum. These are intraband contiguous, intraband non-contiguous, and interband. In the first 2 cases, the component carriers lie within the same defined frequency band, either directly adjacent to each other or separated by some non-trivial distance, that is, some distance greater than just a nominal guard band. In the third case, the component carriers are in completely different frequency bands. Now, one might ask, why should we make this distinction at all? As we discuss a little bit later in the presentation, the interband case, that is where the component carriers are in completely separate frequency bands, this case creates a far greater challenge from a design and operational point of view. In the United States, the predominant carrier aggregation mode will, of course, be the interband case, since there are very few places where large blocks of spectrum exist in which one could place contiguous, much less non-contiguous carriers in the same band. That said, there are plans to reallocate about 120 megahertz of spectrum in the 600 megahertz range sometime in 2015 or 2016. The date keeps moving. And depending on how the spectrum is auctioned off and allocated, it is possible that we could see intraband carrier aggregation at these frequencies sometime in the not too distant future. One of the factors further complicating the use of LTE Advanced is simply the sheer number of LTE frequency bands. There are currently about 25 frequency bands allocated for LTE worldwide, and this is for FDD alone. Looking at the most simple case of only 2 bands, there are about 300 possible combinations of bands that a UE would theoretically need to support in a carrier aggregation scenario. Taking the math a step further, 5 LTE bands, the maximum number of component carriers supported in Release 10 for carrier aggregation, this would yield over 3 million possible band combinations. Now, aside from being completely unworkable from a technical point of view, this is of course highly unrealistic. First of all, it would be extremely difficult to design a device that could communicate on all of these bands individually, much less communicate on all of them simultaneously. In addition, since only certain combinations of bands exist in certain parts of the world, and only for certain carriers, that is, network operators, 3GPP introduced the idea of band combinations, or CA bands. The table we see here on the right of the slide is an example of some of the proposed carrier aggregation bands, which are usually based on requests made by the network operators themselves. For example, we see the CA413 band is, as one might expect, a combination of band 4, the AWS band, and band 13, the upper 700 megahertz band. This list of carrier bands is not set in stone, but it is a good starting point in what we expect going forward we'll see in terms of carrier aggregation. So now that we've discussed the concept of component carriers and bandwidth and how this is all set up, again, we have one primary and one or more secondary carriers. And we've also discussed how these carriers might be distributed at spectrum. Let's talk about how we actually go about aggregating these carriers so we can take advantage of the additional bandwidth that they could provide to the UE. One of the most important things to understand about carrier aggregation is that carrier aggregation only exists when the user equipment, the UE, the phone, the data card, etc., that is, an LTE device, informs the network that it would like to make use of carrier aggregation. The UE connects to the network in exactly the same way as in a standard Release 8 LTE device. Remember that for the purposes of backwards compatibility, every potential component carrier appears exactly, for all practical purposes, as a normal Release 8 LTE cell. This means that all these standard access procedures, things like RATCH, RAR, RRC, EPS bearer setup, etc., all of these work in exactly the same way for normal LTE and for Release 8 phones. What is different and what makes carrier aggregation possible is that once the UE has connected to the network, as now on our slide here, as a normal Release 8 device, it can inform the network of its ability to support carrier aggregation, as we'll see on the next slide, and as a result, create a second connection using the secondary component carrier. Let's take a closer look at the way that the UE communicates its ability to support carrier aggregation and the way in which the carrier provides the UE, the network that is, provides the UE with the information that the UE needs in order to use these multiple component carriers. Again, assuming that both the device and the network are capable of supporting carrier aggregation in the first place. The first step is that the network queries the UE regarding its capabilities. Now, like most other messages involved in carrier aggregation, this is a standard part of the normal messaging used in normal Release 8, Release 9 LTE. The UE, in turn, responds with a message indicating its support for carrier aggregation and the associated parameters. Some of these parameters are more esoteric than others. The two most important parameters in this message, the UE capability information message, are that it's, first of all, this UE category, which among other things indicates support for carrier aggregation, and also the band combinations it supports. These are the CA bands that we looked at a few slides back. These are the most important parameters to look for when you start examining the messages between the UE and the network when you're testing or troubleshooting a UE's ability to use carrier aggregation in the field. Once this pair of messages has been successfully exchanged and acted upon, we have now essentially enabled carrier aggregation in the sense of allowing the network to see that carrier aggregation is supported on the UE side. Now, assuming that the network is able to and willing to provide carrier aggregation, and after some security exchanges, the next step is to send an RRC connection reconfiguration message. This message details the parameters that the UE needs in order to make use of multiple carriers. Now, in terms of complexity, this message is substantially more involved than the UE capability inquiry. But if you were to take a look inside this message, you could see which SCCs are being enabled, as well as information about the uplink control channels to be used. Again, assuming that all of this information is something that the UE is happy with and can act upon, it will, of course, now send an acknowledgement and tell, by means of an RRC connection reconfiguration complete message, that it's ready to use the multiple component carriers. And essentially at this point, carrier aggregation has been correctly configured, and both the network and the UE are set up to take advantage of the multiple component carriers. Let's look at an example of how this happens in practice with multiple UEs. First, we have UE1, which is a normal, plain old Release 8 UE and is not carrier aggregation aware, so to speak. It attaches to cell 1 as a normal LTE UE and is assigned some number of resource blocks, and after which it continues. Of course, the resource block allocation is dynamic, but afterwards it continues its existence blissfully unaware of anything related to carrier aggregation. It's a plain normal Release 8 UE and is connected to a normal cell. This is also true for UE2, which goes through the same process, this time on cell 2. Again, there's nothing about a cell that indicates that it is a carrier aggregation cell from a UE point of view. Looking at the signaling coming from the cell, or looking at the system information messages, or the lower layer parameters of the cell, there's nothing that would indicate to a UE that this cell is actually capable of supporting carrier aggregation. Now, UE3, after attaching the normal way to cell 1, now exchanges the capability information, RRC reconfiguration messages that we saw on the previous slide. Assuming this all goes well and everyone is happy on both sides of it, the result is that now it would have access to both cell 1 and cell 2. In this case, cell 1 is the primary component carrier, or is providing the primary component carrier, and cell 2 is providing the secondary component carrier. Now, PCC is device specific, not cell specific. It's not as if cell 1 is a PCC cell and cell 2 is an SCC cell. A cell provides a PCC or an SCC on a per UE basis. This means, for instance, that two terminals that are on the same network operator could have their PCCs on different frequency bands or on different cells. So let's take a look at UE4 here, which is also a Release 10 UE. It goes through the process of attaching to the network, this time on cell 2, which would be its primary component carrier. And then, after it goes through the capability exchange and the RRC connection reconfiguration, now decides that it can take advantage of cell 1 as the secondary component carrier. Again, it's very, very important to remember about carrier aggregation. That carrier aggregation is essentially a UE-centric feature. It is not a network-centric feature. Carrier aggregation is defined and configured on a per UE basis on the basis of signaling messages, capability information, RRC connection reconfiguration between the UEs and the network itself. Another very important aspect of carrier aggregation has to do with mobility, or what a lot of people would refer to as handovers. Since this webinar is primarily intended for people working in the field versus working in a lab, people actually testing carrier aggregation in the field versus building eNodeBs or UEs, we won't go into a great deal of detail regarding the specific channels that are used and how they're allocated when using carrier aggregation. The very, very, very short version of this is that in carrier aggregation, some control channels do double or triple duty. What that means is that instead of a component carrier having a full set of control channels on every component carrier, the control channels on one of the carriers, the primary component carrier, are actually used to signal information from multiple component carriers, resource allocations, etc. This has a number of benefits in terms of reducing signaling complexity, simplifying the interactions between the UEs, the network, etc. But it does lead to one complication in a practical aspect, especially when carrier aggregation is deployed in the field, and that is, how do we handle handovers? So normally various types of information have to be exchanged before, during, and sometimes after a handover occurs. And the way that this is normally done is over the control channels for that carrier. However, in carrier aggregation, some of the carriers, the SCCs, may not have control channels, and therefore they have no way to exchange this information. The simple solution is that if a UE is using carrier aggregation, if it's connected to more than one cell, then the SCCs have to be released before the handover can occur. Here, for example, a UE makes a connection to a primary component carrier and a secondary component carrier. At some point, their decision is made to create a handover over to a different cell. But what has to happen at this point is the first secondary component carrier, SCC1 here, has to be dropped. Then the handover is done between PCC1 and PCC2 the normal way, the way that it's done in Release 8 and Release 9 LTE UEs. After that has successfully occurred, then the connection is established to the secondary component carrier. And we have the situation again as we had before. Now, one practical but extremely important implication of this mobility scenario is that it can cause a substantial drop in throughput, since all of our SCCs, which are presumably providing us with extra throughput, have to be dropped and then re-added. In situations where you have very frequent handovers, especially in an indoors or a highly mobile scenario, for example, when I'm driving, this can have a very non-trivial and very serious impact on the overall data performance in the network. So it becomes very important to try to minimize, even more so than Release 8 or Release 9, it becomes very important to try to minimize the number of handovers and carrier aggregation, because the number of handovers will have a strongly adverse effect on the throughput that we can see in the network. This leads us somewhat into our next topic, which is how do we provide coverage in a carrier aggregation environment? There are a number of different proposals. There's pretty much a new proposal every week, and ideas on how to provide coverage for UEs that can use multiple component carriers. That is, how do we provide coverage to UEs that can use carrier aggregation? And it's highly likely that there will be no single dominant methodology that will be used for carrier aggregation as it starts to be deployed on a widespread basis. Let's take a look at a few of the more popular suggested approaches to providing coverage for carrier aggregation. The first of these is essentially to try to provide more or less completely overlapping coverage for every band or every carrier in use. This is somewhat roughly depicted in the top diagram. In other words, the cell boundaries for, say, my 700 megahertz and my AWS spectrum would essentially have, as close as possible, 100% overlap. This sounds like, and in many respects is, a perfectly rational and sensible proposal, especially in the case where I can co-locate the E-node Bs, the transmitters, the antennas for each band, since this will obviously make it easier for me to provide identical or nearly identical and overlapping coverage. In practice, however, there are a number of issues that one might run across. The first of these is our old friend propagation. The same power levels from the same sites, perhaps even the same antennas, will not necessarily propagate the same distances or in the same manner, especially in the presence of foliage, buildings, terrain, etc. There's a saying, of course, that the problem with coverage is that most people don't live in fields. If everyone lived in an open field, coverage would be a lot easier. And the place where you have the most subscribers tend to have the most difficult terrain and coverage issues. Now, naturally, this phenomenon in terms of non-equal propagation, non-equal coverage, is more pronounced for interband than for intra-band operation. For example, it would be much more difficult between 700 megahertz and AWS versus two carriers at 600 megahertz. But in the United States, for the time being, carrier aggregation is almost exclusively an interband phenomenon, and so this is what we normally will have to deal with. Depending on who you ask, providing in-building coverage for multiple carriers is either much easier or much harder than for the outdoor macro scenario. In-building systems, small cells, DAS, etc., have a huge advantage in that they allow one to more closely control and tweak the coverage where they're needed. So in a sense, it does make it easier for you to provide roughly equivalent coverage on each of the component carriers. On the other hand, having lots of small cells can also complicate matters by requiring more frequent handovers. And as you may recall from the previous slide, frequent handovers can lead to severe throughput issues, and it's something that we would very much like to avoid if possible in a carrier aggregation scenario where a UE is making use of multiple carriers, since again, the secondary carriers will have to be dropped every time a handover occurs. Ultimately, like so many other things in the network operator world, the relative pros and cons of a particular approach are best judged in actual field trials and deployments. And therefore, at this point of the webinar, I'd like to turn things over to my colleague, Jeremy Cline, who will go into more detail about the important aspects of actually testing and troubleshooting carrier aggregation in the field.
All right. Thank you, Paul. As you've probably realized by now, the biggest theme behind carrier aggregation is gaining as much throughput as possible. After all, it was the main driver behind LTE Release 10. In addition to that, we know that customers easily notice two major things about their phone: the data speed they get, and of course the battery life, which happens to be something we'll cover in a few slides from now as well. Since throughput is the top priority, testing and troubleshooting carrier aggregation becomes increasingly important. With that said, there's three factors to consider when testing carrier aggregation. First is the device itself. Does the device support carrier aggregation in the first place? Is that determined by its SIM card, or is that a firmware capability? Does the device's hardware support the right band? Well, these are all great questions to ask. In addition to that, what about the network itself? Well, in general, there are no carrier aggregation towers or carrier aggregation bands, as Paul had covered before. The network infrastructure is the same, but what becomes important is individually testing each component carrier and then comparing those results against what you get by testing bands aggregated together to see if you're truly getting increased throughput. And then, of course, there's the environment. It always has an effect on testing. Is there interference affecting your primary or secondary band? How does the UE know which band to pick? Is that determined by the tower or the phone's firmware, or maybe even both? Also, legitimate questions to be asking yourself. All these are valid, and the takeaway here is that there are a lot of considerations to be aware of when troubleshooting carrier aggregation. To ensure customer satisfaction, it's critical to develop a good testing methodology. So let's dive a little deeper about testing devices. As mentioned before, the device must be able to take advantage of multiple carriers in the first place. We first need to ensure that the phone has the correct radios, firmware, and antenna. You can test these UE configurations in the lab, but be aware that testing in the field is a whole different environment than anything that can be planned out in the lab. What I mean by this is there's going to be different levels, potential interference, etc. True field testing thus becomes absolutely crucial in determining whether the device performs carrier aggregation correctly or not. As you might imagine, carrier aggregation leads to a tremendous increase in UE complexity. We're already cramming as many radios as possible into the latest phones, but now we're also asking the phone to transmit and receive on more than one frequency band at a time. This means that we're providing more capability, which in turn means more power is required. As is always the case, the problem is customers have expectations when it comes to battery life, so we certainly can't afford to have noticeably less battery life than we did before. Additionally, the phone needs to have an antenna configuration that supports carrier aggregation. This requires a more complex design, especially if you consider the proliferation of MIMO. And what about the front end of the phone? How wide should that be? The widest LTE channel bandwidth is already 20 megahertz, so probably wider than that. Well, that leaves us with the real question. How wide is wide enough when we're aggregating more than one frequency band? Well, going forward, this becomes a more and more complex question to answer. Next, we have to consider the signaling of the phone itself. If the phone is release 10 or later, it ought to be communicating the correct layer 3 messages to the tower to say it supports carrier aggregation. I think Paul mentioned this earlier. Similarly, the tower needs to relay the correct messages to the UEs to say it supports carrier aggregation as well. Well, then, of course, there's handover considerations. If a UE is in an area where CA is supported, what happens when it leaves that area? Ideally, the phone must be able to deactivate and continue operation without dropping the call. This is something that needs to be tested to ensure customer satisfaction. When determining what throughput can be expected, you'll want to determine a UE's performance on a per band basis because each UE will perform differently, perhaps substantially, depending on which bands it actually locks onto. This could be a result of the UE's design, such as its antenna configuration or power limitations, for example, or alternatively, it could be a function of the network, whether that be a dynamic coverage or capacity issue, or maybe even an unexpected interference issue. To determine what's really going on, we need to test each given band separately to see what throughput we get on a per band basis. Well, one way to do this would be to test one band at a time with a single device, come back after launch, test another band. But ideally, we would want to utilize testing solutions that exist today that allow multiple devices to be used at once, such as in a backpack or other enclosure. In this manner, each individual device can be forced to a particular band and tested simultaneously. This not only saves you time by preventing multiple walks, but more importantly, it ensures that each band was tested in the same RF environment at the same time. In some cases, forcing to a particular PCI may also be required for coverage and or neighbor testing. Now, I've been referring to battery life considerations a number of times so far, and it truly is a growing problem as UEs become more and more complex. With carrier aggregation, we know that operation on multiple bands requires multiple transmit chains, which of course increases the power consumption. So how do we monitor this issue? Well, one way is by theory. There's engineers hard at work every day optimizing power amplifiers, but with regard to carrier aggregation, it's impractical to optimize those for the wide frequency ranges that we need. In the end, we want to make the phone use less power, but provide more capability. This is much easier said than done, and it's always the case. So in the lab, what manufacturers do is they remove the phone's battery and attach a power meter directly to the battery contacts to monitor voltage and current. Well, obviously, this isn't going to work in the field because we can't have a power meter hanging off of a phone. So how do we test the battery life? Well, the closest thing we can do is monitor and record the battery level displayed by the phone over a duration of a number of tests. To do this, you start by performing a test on one band, record the battery level the entire time, and then switch the phone over to a different band. Measure the battery life during that test as well, and then compare your results. This approach is the most advantageous because we can compare the amount of battery life lost during each test. To determine if a phone is carrier aggregation capable, we need to analyze the signaling between the UE and the network. As mentioned before, the support for CA or certain band combinations will depend on the built-in hardware and firmware of the UE itself. The UE needs to be correctly signaled to the network, and this can be verified by inspecting layer 3 messaging, specifically the UE capability information and RRC connection reconfiguration messages. As an example, look at the layer 3 messaging in the screenshot here. If we dig down deep into the LTE RRC UE capability information message, we can see that this particular phone is a Release 9 device. Well, in this particular example, we found out why the phone is not performing carrier aggregation, because we know it's a Release 9 device, and Release 9 UEs have no support for carrier aggregation. Even if we didn't know that, we can tell because the UE never goes on to tell the base station that supports the feature via layer 3 messaging or vice versa from the tower. Another factor in testing carrier aggregation is the network itself. From an RF standpoint, I mentioned earlier that there's no such thing as a CA base station. The same downlink carriers used in non-CA LTE are the downlink carriers used in CA as well. Each of these downlink and uplink carriers must be tested individually for common parameters such as received signal strength indication, or RSSI, reference signal receive power, or RSRP, and error vector magnitude, or EVM. But you don't want to stop there. With carrier aggregation, all potential carriers need to be tested simultaneously as well. At this point, testing for 3 carriers is pretty much it, because at this point, the initial LTE Advanced rollout only shows pairs of bands. Looking at more than 3 bands doesn't make sense right now, but going forward, this will certainly change. And as time goes on, this will create the need for more complex testing, as you might imagine. Standard LTE measurements such as channel power and occupied bandwidth can and should be used on each of the component carriers. Inter-band contiguous carriers may complicate measurements such as occupied bandwidth, however, because of some gray area in current methodology. Right now, we typically measure 10 or 20 megahertz at a time because that's what's done for LTE channels. But if we're combining multiple interband carriers that total up to 40 megahertz or beyond for carrier aggregation, how do we test this successfully? Well, as an example, look at the 2 adjacent component carriers in this screenshot. As you can see, 99% of the power is within the occupied bandwidth of 20 megahertz. Well, if you measured only 10 megahertz at a time and then added up the results, you wouldn't get the same answers if you measured the entire aggregated span instead. In this example, we have 2 intra-band carriers, but when trying to perform the same measurement on inter-band carriers, our answers will be skewed by the same theory. Going forward, this will be a testing challenge. For example, when the 600 megahertz band is deployed, if you have a 40 megahertz chunk, how do you measure it? Make sure all of your measurements methodology take these considerations into account. When LTE came out, we had a similar problem that we do today. How do we fill the pipe, if you will, enough to test peak throughput? With carrier aggregation, this problem is even worse because the highest throughput possible should be higher than that of what we call standard LTE now. In reality, there's no servers out there that will fill up the pipe enough to give us our highest throughput, so what do? Well, one way to change this is we got to change our methodology a little bit, again, and try doing simultaneous downloads from multiple sources. Instead of depending on one server to provide all of the throughput, we instead divide the burden among several different websites, FTP servers, etc. Take a big file, put it in a couple different places, and use that to pretend like you're downloading from one big server. That's about the best way to do this. When measuring aggregated data rates, we are most interested in the overall actual throughput. If I take 2 phones, for example, and download large files on 2 bands individually, take a third phone that's CA capable and do the download doing the 2 bands simultaneously like I just mentioned, do I get the same number? Well, ideally, yes. We'd like to see that the aggregated throughput would be equal to the sum of each of the throughputs from each of the component carriers, but in reality, this is unfortunately not the case. Due to several implementation and environment-based reasons, we're lucky to see about 85% of aggregated throughput efficiency. To figure out where the bottleneck is, testing individual component carriers against the aggregated component carriers will help determine where the potential issues and or imbalances are coming from. One of the factors I mentioned earlier with regard to carrier aggregation is the RF environment itself. In some cases, some of the component carriers are harmonically related, thus creating the potential for RF interference. As an example, let's examine band 4 and band 17. By looking at the frequency allocations for each band's uplink and downlink, we can see that the third harmonic of band 17 uplink falls into band 4's downlink allocation. Well, for now, we don't see this as a huge problem because the uplink power is significantly less than the downlink power. But as the frequency spectrum evolves over time, what happens if a high-powered downlink signal creates an nth harmonic that falls into the uplink allocation of another band? Well, this is much more detrimental and is something to pay especially close attention to. Going forward, having a good methodology for this kind of testing with interference is also going to be very important. Be prepared with the right filters to verify these types of issues. They come in handy. And what about interference? That leads us to another major topic of consideration. In any kind of RF environment, the effect of interference can never be ignored. With carrier aggregation, any kind of external RF interference can and will affect any of the bands, thus affecting your overall throughput performance, which we know is probably the single most important parameter here. Single wideband interferers such as jammers, oscillating bidirectional amplifiers, or BDAs, and cable egress can affect multiple component carriers that are intra-band. For interband, however, it's unlikely that a single interferer would span wide enough to affect multiple bands at once, with the one exception being harmonically related bands such as band 4 and band 17, like we just saw. Wideband antennas are an excellent choice to check for interference in multiple bands at once and are more convenient than using multiple single band antennas, as you might imagine. One more thing before we move on from this slide. One interference related question we get a lot about is testing for passive intermodulation, or PIM. As deployments move indoors like DAS systems, microcells, etc., that means we're dealing with lower propagation distances, and that diminishes the likelihood of PIM, so as we go forward, that's not expected to be a common interferer. To wrap up today's webinar, Paul and I would like to leave you with 4 major takeaways. First, carrier aggregation allows higher throughput and more flexible network dimensioning by combining different component carriers. This functionality is UE initiated, and there are numerous performance-related considerations to take when it comes to the UE's antenna design, power requirement, signaling, and overall capabilities. Traditional LTE measurements are still important because there are no such things as carrier aggregation towers or carrier aggregation bands, and overall performance may not be a linear combination of each component carrier. It is necessary to test each carrier individually and simultaneously. Throughput is single-handedly the most important consideration from a subscriber's point of view when it comes to carrier aggregation, with battery life in a close second. So developing a methodology to test these factors is going to be critical going forward. Thank you for your time and attention today. Paul and I hope you enjoyed this webinar. And at this time, I think we have a few minutes to take some questions.
Hi, thanks, Jeremy. This is Kyle again. Yeah, we had quite a few questions come in, so we'll jump right in. And I want to encourage all of our attendees to please submit your questions, and we'll try and get to them. If not, we will forward a copy of them onto our presenters. Anyways, the first one we had come in is, how do you test multiple carriers simultaneously?
Well, there's a couple of different ways that you can test multiple carriers simultaneously. Well, there's really 2 categories of that. One is being able to test multiple carriers simultaneously on a single device. That is a device that's actually able to take advantage of multiple carriers. The other one is to test multiple carriers simultaneously by examining them as individual carriers, let's say individual release 8 carriers. Now, in the first case, if you're trying to test that a device can look at multiple carriers simultaneously, you obviously can look at the signaling messages to make sure it's actually doing that. The UE should have some kind of feedback or information that shows it's using multiple carriers. And ideally, if you're using multiple carriers, you should be getting a higher aggregated throughput than you would for a single carrier. The more difficult case, though, is how do you test the 2 component carriers at the same time? I think Jeremy alluded to this. What you don't want to do is walk through a building today and test 700 megahertz, walk through tomorrow and test 1700 megahertz, and then make some conclusions based on that. Typically, if you're going to be testing multiple carriers simultaneously, you're going to need, as individual carriers, you're going to need multiple devices. And ideally, you want these devices to all be synchronized and do the test at the same time, because the RF conditions can change, the capacity issues that you may have may change. There'll be more or less loading depending on which time of day or day of the week you might be doing this. So again, typically what you're doing, if you're trying to verify the individual performance of the carriers, you would need multiple UEs or multiple devices. If you're trying to verify the aggregate of multiple carriers, then you can do that on a single device.
Great, thanks. The next question we had come in is, what's the best way to fill up the pipe?
Okay, covered that a little bit in one of the slides, but in general, you know, there's not going to be a server out there that is capable of pushing hundreds of megabits per second down the pipe, if you will. So I think one of the best ways that I found to accomplish that is, you know, go to at least 2 different servers, put some large files on there, you know, to fill up your cycle time or your job time, and try to simultaneously download those from the two or more sources, and that effectively becomes a bigger pipe, if you will.
And the next question we had come in, why is the second CC referred to as the cell 2? Is this because the second CC needs to be assigned a different PCI?
Oh, no, absolutely not. Actually, the point of that slide was cell 1 and cell 2 are just simply for the purposes of explanation. No, absolutely not. Any given PCI, any particular cell can serve as a primary component, or can serve primary component carrier, secondary component carrier, or any combination thereof. This is the beauty of carrier aggregation, is that it's not something that you program the cell to do. It's not as if you say this particular PCI, this particular cell is always going to serve up primary component carriers, and this one's always going to serve up absolutely not. The flexibility, and I think on that slide I showed where you can have one UE that's using cell A, cell 1, whatever you want to call it, as its primary, and cell B as its secondary, and then you can have another UE that's doing it the other way around. In other words, it's using cell A as its secondary and cell B as its primary. So no, that again is part of the beauty of carrier aggregation, and it's done on a per UE basis. The UE keeps track of what's the primary and secondary cells defined for that particular UE, not for all cells or for all UEs on that cell.
Great, thanks for clearing that up, Paul. Another question we had was about handover and interband, and if you can explain that a little bit more.
Sure, handover and interband. So anytime you have a handover, the handover really does not matter so much whether it's interband or intraband. I'm not sure if the question's about if there are any differences between that or not. What is a rule, though, is in carrier aggregation, if you're going to do a handover and you have secondary component carriers, you must drop all of your secondary component carriers before you hand over the primary component carrier, and then you can re-add the secondary component carriers. In the worst case, perhaps a silly case, but it could happen, is that you could actually have a primary carrier, multiple secondaries, drop all the secondaries, hand over the primary to a different cell, and then add back exactly the same number of secondary component carriers from the same actual cells. Again, silly case, but there's nothing that keeps that from happening. And again, this is why we want to minimize handovers in LTE Advanced, because every time you do a handover, you're going to lose all of your secondary component carriers. And you can imagine someone who's running an application that consumes a large amount of bandwidth, maybe some high-definition streaming video, and they have a handover, well, they're going to lose a huge part of their bandwidth. The video may pixelate or drop back down to a lower encoding type, and they're not going to be happy. And from their point of view, especially if they're stationary, they'll have no idea what went wrong. And for them, they'll say something went wrong with the network. So again, a really important reason that you have to optimize the network and do your capacity planning such that you minimize handovers for UEs that are currently connected to more than one component carrier.
Great. Next question. Can the PCC and SCC be transmitted from the same site, sector, and/or antenna?
Well, there's nothing that keeps you from sending them from the same antenna. I mean, there are plenty of multi-band antennas. For example, my primary could be 700 and my secondary could be AWS. And those, you could have a dual band antenna that can transmit both of them. There's no physical reason why not to. As a matter of fact, I highly suspect, and again, this is implementation specific, but I highly suspect that a lot of network operators are going to leverage their existing infrastructure. Maybe not the antennas necessarily, but certainly the sites themselves, and have multiple component carriers, again, coming from those sites. And again, keep in mind that you're not really sending component carriers, you're setting up cells, and at the time the UE requests or announces its ability to do carrier aggregation, it's given that reconfiguration. At that point, it becomes a primary or secondary component carrier. There is no such thing as a primary or secondary component carrier until the UE decides to handle, or is instructed to handle, each different cell in that manner.
And we had a related question asked about that. So if the UE is CA capable and has two carriers, how is the choice made about PCC and SCC?
Well, the choice is kind of made for you in the sense that when the UE connects to the network, when it does its RATCH, RAR, and it does everything else that it needs to do in order to connect to the network, the same way that a normal Release 8 UE would do. At that point, where it is originally connected to the network, that is the primary component carrier. So any additional carriers that are configured for it as a result, again, of the capabilities, inquiry and exchange, and the connection reconfiguration, at that point, those would all be secondary component carriers. Now, you could, I suppose, if you were clever and if you saw some value in it, you could configure the UE to prefer certain cells over other cells, a PLMN search, for example, where you say, I want you always to connect to 700 first if a 700 megahertz cell is available. In that way, you could kind of force the UE to always have its primary on 700, and then secondaries could be always AWS, for example. In that sense, there are ways that you could kind of make the UE, trick the UE into preferring a certain band for its primary component carrier. But again, what really makes the primary component carrier ultimately is which base station, which eNode B did it connect to first. That's going to be your primary component carrier.
Thanks. We had a question about one of the slides mentioned EVM, and the question is just explaining what EVM is and what the importance of it is.
Well, EVM is error vector magnitude. As you're probably aware, in transmitting data in LTE, there are 3 different MCSs, modulation encoding schemes. There's QPSK, which is 4 symbols. There's 16 QAM, which has 16 symbols, and 64 QAM, which has 64 symbols in the downlink. In the uplink, you have, right now, you have a QPSK and 16 QAM. And what happens is if you think of them as constellations, as sort of think of an XY coordinate plane and all these little dots, and each dot represents a state. What you would like to do is to have your signal fall neatly onto one of those points to represent one of those states. In the real world, that doesn't always happen. As a matter of fact, it pretty much never happens. The points don't exactly fall on the ideal point, so they're a certain distance away. They're a certain X and Y away. And the distance that they are away, the vector, the error vector magnitude, in other words, how far that is what EVM is. How far away is this particular point from the ideal point in this constellation? Now, from a practical point of view, the LTE standards actually define certain acceptable thresholds for EVM for different modulation types. As the modulation order gets higher, for example, 64 QAM versus 16 QAM, the requirements are more stringent because at 64 QAM, there are a lot more different points you could be, so you need to be a lot closer to avoid accidentally falling onto another point. Now, as a practical matter, EVM is one of the things that we, of course, would like to measure in our network, LTE Advanced or just regular LTE. And again, the LTE standards do specify certain minimum levels of EVM. The reason that EVM is important is EVM can be due to a couple of different things. EVM could be due to problems within the base station itself. The transmitter could be problems in the UE receive chain. EVM can also be caused by interference or noise in the transmission path. So if you're doing an over-the-air type measurement and you see high levels of EVM, that often is an indication that perhaps there is interference or there's some other issue. And again, if the network in LTE dynamically detects that there are too many bit errors or problems related to EVM, it will reduce its modulation encoding scheme. So instead of using, say, 64 QAM, a lot of little points, got to be very precise about where your signal falls. First, it may cut down to 16 QAM or QPSK, where you only have 4 points. And while this in itself is relatively easy to do, the problem is that the lower order modulations will produce lower throughput. So for 2 reasons, then, you want to watch EVM because, 1, high levels of EVM will typically cause you to fall back to lower order modulation, which means less throughput, which is what we all want, it's more throughput. And the other one is it can be indicative of problems either with the equipment itself or with the RF environment, so over-the-air things, interference, for example.
Great, thanks. So while we're kind of on the topic of LTE and how this plays in, another question we had is, will carrier aggregation interfere with normal LTE operation for non-CA enabled devices?
It shouldn't. I say that it shouldn't for this reason. In the sense of, will it interfere in the sense of carrier aggregation signals interfering with release rate signals? No, because they're all the same signals essentially. I mean, there's no way that you can look at it and say, oh, that's a carrier aggregation UE transmit or UE using carrier aggregation transmitting versus one that's not, just based on the signals themselves. Interference, though, could mean a couple of different things. In an RF or signaling level, probably not. I don't really see how it could. It could interfere in terms of how the network is dimensioned. For example, if I have a lot of frequent handovers or if I'm dropping and adding carriers, I mean, will this cause disruption in the network? Hard to say. That's really a function of the network itself. Will the presence of carrier aggregation UEs starve the network or the non-CA UEs for bandwidth? Again, shouldn't. It's possible. Again, these are more network design issues and capacity planning issues. But in terms of a pure technical UE communicating with eNode B and vice versa, it should make no difference at all.
Sorry about that. Great. We have time for really just one more question. So for the last question, you've touched on it briefly. Is there any way to force UEs to use or not use carrier aggregation?
Well, yes and no. Again, remember that in carrier aggregation only exists in the context of a UE. If you had a whole bunch of base stations that are on and no UEs talking to them, there is no carrier aggregation. There's no way to tell, standing out in the field with your equipment, that, oh yes, carrier aggregation has been turned on in this part of town. There's absolutely no way you can tell that. So how do we allow UEs or force them to use carrier aggregation or not force them? Again, this involves two different parts. The first of all, the UE has to announce via the capability information. So the network queries the UE. What kind of UE are you? What can you do? The UE responds back, I'm this kind of UE, I'm this category, and I support these bands. So if the UE doesn't report that, or if, first of all, the UE is not capable of doing that, but if the UE doesn't report that information back, then obviously the network is not going to offer carrier aggregation because it assumes the UE is not capable of taking advantage of that. Now, whether this is a parameter that you yourself as the user, the subscriber, could control, that's hard to say. I know that, for example, that on my phone, I won't say which phone it is, you can probably guess, there's a enable LTE little toggle switch. So I guess that if I wanted to, I could turn off LTE. Perhaps when I have a CA enabled phone, it will have a enable carrier aggregation switch, so I could choose not to. I can't think of a good reason why I wouldn't, again, because except maybe I'm trying to avoid downloading massive amounts of data now that I have a bigger pipe. But so on the one hand, you could inhibit carrier aggregation by simply telling the UE, don't tell the network you're capable of doing it, and then the network will not offer that to you. On the network side, you can keep UEs from being able to use carrier aggregation by, of course, you inquire, and the UE replies that, yes, I'm a UE capable of doing carrier aggregation. But then the network simply refuses to provide you any information that you would need to take advantage of carrier aggregation. In other words, that RRC connection reconfiguration message that it would send out, it simply either doesn't send it out or it sends it out with information that the UE is not able to take advantage. It does not specify in that message, and it's a very long message. It does not specify in that message which secondary component carriers are available or the information that's needed to connect to them. So really, it requires cooperation on both sides. The UE has to explicitly state to the network, yes, I am carrier aggregation aware, which I guess implicitly implies that you would like to use it. And then the network, after being informed of this, then has to tell the UE, okay, here is the information that you need to take advantage of carrier aggregation. And whether that's controllable on the network side, I'm absolutely sure it is, or it ought to be. On the UE side, will there be some toggle switch enable carrier aggregation on the phone? That's hard to say. It probably will be device specific. I wouldn't be shocked to see that, but I would be a little bit surprised to see users have the choice of whether or not they want to enable CA or not.
Great. That's about all the time we have. I want to thank everyone for attending Understanding and Testing Carrier Aggregation in the Field, presented by Rohde Schwarz. Again, our presenters today were Paul Denisowski and Jeremy Cline, application engineers at Rohde Schwarz. Paul and Jeremy, I just want to thank you guys for a great presentation.
Thanks, Kyle, and thanks everyone for attending.